Okay, now we're going to be looking at mixed radicals. Radicals are this symbol right here. Usually it's square roots, but it doesn't have to be. We're going to do cube roots and fourth and fifth and sixth roots, but typically we've learned it as square roots. And so one of the things to keep in mind is that when you have two numbers that are multiplying each other, you can kind of separate them like this. So square root of a times b is the same thing as square root of a times the square root of b. You won't necessarily see that, but it is baked into what we're about to do. And more importantly is what you see here. And so you don't see that it's a square root symbol. So we can get that. This is a square root here. And in the absence of any number, we know that the number is going to be 2. And so what we're going to see here is that we're looking for it to get two A's. We're looking to get them into pairs, which we've already done before. So we're looking them to get into pairs. And if you do, you can take that pair out and it just becomes a single A. And that's because when the pair comes out, you can see it here, there's 2 of them, and the 2's essentially cancel, leaving just the A. So you're looking for pairs. And so maybe that's what, let's write that down here. You're looking here for pairs. Just a reminder of what we did earlier. So let's take a look at how this works, because we know some square roots. Square root of 64 is 8, but what happens if you don't have, it's not a perfect number like 64? Well, 32, well, that's going to be 16 times 2. And so we do this prime factorization tree. 4 times 4, bring down the 2. And that's 2 times 2, and then this is 2 times 2, and there's an additional 2. So you're looking for pairs. So there's a pair of 2's and another pair of 2's. 2 times 2 is going to be 4. And then you can, what's left over? Well, just a single 2 is left over. So that's how we do this. So let's try another one here. 40, I like the one to the 0 because you can break it up to 4 times 10. I like the 10s here. Now 4 is going to be at 2 times 2. 10 is going to be at 2 times 5. So we're looking for pairs because it's a square root. So we're going to find pairs. There's a pair of 2's. And that's it. And then on the inside is kind of what's left over, our non-pairs. 2 times 5 is 10. Those are our non-pairs here. Let's keep going here for 80. I like, again, the zeros here because that's an 8 times 10. 8 is going to be a 4 times 2. And this is going to be a 10 is going to be a 2 and a 5. And that 4 is a 2 and a 2. And we can bring down this 2, 2, and 5. So what we're doing here is we're getting this down to our prime numbers. So 2 is a pair, another pair. 2 times 2 is 4. And left over is a 5. So this is called prime factorization. It says trees, and we use prime factorization here to reduce these radicals, these square root symbols. Now 110, that's nice because it's 11 times 10. 11 can't be reduced, but 10 can be. It's 2 and a 5, and the 11 could just go here. Any pairs? Actually, there's not. So there's no pairs. So if nothing can come out, then it's just what it originally was, which is the square root of 110. Nothing changes. It was already simplified as much as it could be. Okay, that's interesting. Okay, let's look at this. 360. Oh, I like this one because it's a 10 again, so 36 times 10. This right here, that's a 9 times 4. And 10 is 2 times 5. And that 4 will be a 2 and a 2. That 9 will be a 3 and a 3. And then the 2 and the 5 can come on down. So we're looking for pairs here. Pair of 2's, pair of 3's. 2 times 3 is 6. And my leftover is 2 times 5, which is 10. 480. That's a 48 times 10. 48 is going to be a, I don't know, but 12 times 4 maybe. 10 is a 2 and a 5. 12 would be a 4 and a 3. And this 4 can be a 2 and a 2. And this 2 and 5 can come down. And a 4 is a 2 and a 2. 3. And then a bunch of 2s and a 5. Okay, good grief. What do we have here for pairs? So a pair of 2s, another pair of 2s, for a total of 4. And left over, 2 times 5 is 10, and a 3. 10 times 3 is 30. So 4 and the square root of 30. Okay, so we got 2 more. This is good. This is another one of those 81 times 10. 81 is going to be a 9 times 9. That 10 will be a 2 and a 5. Those are reduced, but the 9s can both be brought down to 3 and 3. So that is a pair and another pair. So 3 times 3 is 9. And then left over is 2 times 5, which is a 10. Okay, lastly, 1875. Now I know it can be divided by 5. I don't know what it will be, but I am actually just going to try 25. So can 25 go into 1875? Well, 25 can't go into 1, it can't go into 18, but it can go into 187. And it can go in 7 times. 25, 4 times is 100, and another 3 times is 75. So 175. And I can subtract those. That gives me a 12. Bring this down. 25 goes into 125 5 times. 5 times 25 is 125, which is 0. Okay, so this can be broken up to 25 and 75. Well, 25, that's obvious. That's 5 times 5. 75 is 25. How many times does 25 go into here? 3 times. So 3 times. And then, so the 5 can come down, that 5 can come down, that 3 can come down, and that will be a 5 and a 5. So what do I have for pairs here? I have a pair of 5s and another pair of 5s. 5 times 5 is 25. Notice I don't add them, I multiply. And the leftover is a 3. So 25 square root of 3. Okay, so those are the first 8 questions. And then the next video we will do example number 2.